The PCB, or printed circuit board, has become the standard form factor for all electronics in the modern age. I took these two out of a computer monitor, but literally everything that I walked past that had a battery or plugged into the wall, my refrigerator and my appliances, Bluetooth headphones, even my little microphone here. This tiny microphone has a Bluetooth receiver, it's got an antenna, a battery, and a little printed circuit board with capacitors, resistors, and all of these little microscopic electronic components that need to work together. Now, technically speaking, the PCB is just the board and the copper traces or electrical circuits that are on the board. And then on top of the PCB, we add all of these other components that need to communicate with each other. So through the magic of editing, we're going to jump on an airplane, fly halfway around the world, and tour one of PCBWay's manufacturing facilities where they make these amazing little boards. Regardless of the size or complexity of your project, they pretty much all start with a prototype. You take a breadboard, or you just take the components that you want to connect together electrically. You get regular wires and you plug them in and make sure that your design works. But once you have formed this circuit, you often also want to make it smaller, lighter, more compact, more robust. And especially if you want to make tens of thousands of these very easily, you're going to get those kind of benefits from turning it into a PCB. And this is basically what PCBWay does. They take in orders from large corporations all the way down to individual makers who just want to get a handful of PCBs or maybe even just one PCB. You send your design files to PCBWay and they turn that into an actual PCB. There's all sorts of software available to help you design your PCB. Some of that software is free, so I'll put some links in the description to YouTube videos like this one from Great Scott, which will show you how to design your own PCB. But once we have a design, we're going to hand that over to engineers here in the PCBWay office so that they can review it and make sure that this PCB can be manufactured. This young lady is Elaine. She's going to be guiding the PCB tours, and Eric, the guy standing in the back, he'll be helping me tour the CNC manufacturing, which we'll talk about in another video.
These are engineers who processing or review the orders of our 3D printing and CNC machine, extrude metal fabrication, etc. And this is when our customer they have their assembly order, so boneless, so they will purchase or source the component that is our customer provide. This is so that's what our assembly parts.
If you remember earlier, I told you the PCB is basically the board and all the copper traces, both on the inside because you can have multiple layers and on the outside. But then on top of the board, you will solder all of these components that need to be connected together electrically. And that's what she's talking about here. That's what these guys do. They source the parts from the BOM list or bill of material. So at this point, we've reviewed the files to make sure that this PCB can be manufactured. We've ordered all of the auxiliary parts that need to go on top. Now we can head over to the PCB factory and actually start putting together some real PCBs.
Manager John?
John?
Yeah, Jeremy. This is Jeremy.
你好。
他可以说一点点中文。
我可以。
Jeremy? Okay, let me show you. I think it's fine, Okay.
Oh, wow. Okay. Oh, yes, please. Thank you. So heel in.
Yeah, right.
And just pull it out.
Yeah, pull it out.
All right.
Okay. This is the very first steps. Class cutting area. Because this is our raw material, and we need to cut it into the desirable pieces.
Okay. I don't know if I caught that on camera, but there's a saw blade that comes up and goes straight across.
It comes out in four, and then we need to process the corner. You can see the difference. It's like an arc, and this is very square.
Okay, Jeremy, this is the second step, mechanical holes, which we also call drilling. So these all drilling machines.
All these rows here?
Yeah, all drilling machines. And this, except this one. This one is for after drilling, and this will double check the drilling part.
Okay.
Yeah, so we
the
can
quality
check.
control is here.
Yeah.
Okay, yeah, quality inspection.
For quality inspection.
Yeah.
Okay, this is already drilled, you can see. Already drilled. This is aluminum and this is the PCB. So like this machine, drilling the same board. So there are 1, 2, 3, 4, 5, 6 drillers, right? All for one kind of PCB. Yeah, so which means one machine can only process one kind of PCB. Yeah.
So these are all drill bits here for drilling the holes?
Yes.
Does it automatically change the drill bits and like drill the additional holes?
Yeah.
Okay.
So this drilling, before it starts to work, we need to program it.
Okay.
Like computer control. You can see the computer. See, and they will control the driller to drill the holes specifically based on our customer's design.
These are really big. Is each sheet one PCB or is that multiple PCBs on one big sheet?
Multiple PCBs in one sheet.
Okay.
Yeah.
Okay. So after watching them do this several times, I realized there are actually far more PCBs being made here than I initially thought. This is like a wasteboard on the bottom. Then he's going to stack these PCB blanks, which are usually fiberglass with copper on both sides if it's just a double-sided PCB. It gets more complicated with a multi-layer PCB, but we'll come back to that. So these PCB blanks are also being stacked on top of each other, and you're going to drill through the entire stack. But within each panel, there are actually multiple PCBs all laid out together. They do this for efficiency. Sometimes it's the same PCB replicated over and over, and sometimes it's other PCBs designed that have a similar layout and fit well within this panel. This speeds up manufacturing. So not only are there multiple PCBs within a panel, there are multiple panels stacked before they put this aluminum wasteboard on top, which is what you see him doing now. They drill through all of these at the same time, and this machine can do 6 sets all at once. So for example, if each panel has 9 PCBs on it, you stack them 4 deep, and then you got 6 stacks. That's over 200 PCBs all being drilled at the same time. Most of the boards I saw had way more than 9 PCBs per board. Like I said, it's a lot of PCBs. At this stage, we're only drilling holes. These holes are important for connecting the various layers together and also connecting components on the opposite side of the board with the front of the board. Near the end of the process, these boards will all go to a milling machine to be separated from each other. It's difficult to see in the video just how fast it's punching out these little tiny holes. The tool change is fully automatic. It will pick up these ultra tiny drill bits, automatically check that it's picked up the right tool and that it's not broken, and then plunge these holes out at an unbelievable rate. The drill bit is spinning at over 150,000 RPM, and it's just astonishing to see it punch these holes so quickly. In the milling area, he told me that the end mills go down to 0.6 millimeters and the drill bits 0.15 millimeters. So at this stage, we have a fiberglass panel with copper glued to both sides and a bunch of holes in it. To add your design to the board, we need to add copper to the holes so that we can get electricity to flow through the whole board, and also remove the unwanted copper so that you only have the copper traces that are part of your design. The next several steps are actually pretty hard to visualize, so I made this really simple 3D model to show you how the board changes after each step. As you can see right now, the holes don't have any copper inside. To get the final thickness of copper, we want to use something called electroplating. Except electroplating doesn't work on the holes because there's nothing conductive there, it's just the fiberglass. So we do Electroless copper deposits or Electroless plating with these chemical baths first, and that builds up a thin layer of copper inside the holes, making them conductive. This is just literally the boards being dunked into a series of chemicals to add the copper, wash the boards, on and on. Both of these processes look very similar visually, so I'm kind of mixing the footage here, but you get the idea. A robot takes the panel, drops it into a solution, lifts it, drops it into a different solution over and over again to get the desired results. But there is one step in between. The Electroless plating goes on the entire board, but the electroplating is only done to the copper traces that we want in the final design. So we actually need to add the design to the board first before we do the electroplating. I'm going to show you all the steps as it was explained to me. And along the way, I'll use my 3D model to help you visualize what's happening inside of all these chemical baths. At this point, we just finished the Electroless copper plating.
You know, the gap files contains the information for the PCBs. So we need to do the plating, which is upstairs. This is the board with that's gone through the Electroless Cooper deposition.
Okay.
Yeah, so, and this line is some preparations before the pattern image. This line with two purposes. First one is to remove the oxidization, and the second one is to toughen the surface to make sure the dry film will be put onto the board.
Okay.
Yeah.
To apply the dry film to the board, the room needs to be exceptionally clean. They don't want any dust or hair or debris to get underneath the film that they use to develop the image on the board. So we go through this cleaning process where we cover our clothes, cover our hair, and then we walk through a chamber to remove any final dust from our bodies before we walk into the clean room. All right, we're ready to go. Doing this is way more fun than it should be. All right. The dry film that they apply to the boards in this room is blue light sensitive. So to keep from developing the film prematurely, all of the lights in this room have this yellowish color. They weren't laminating any sheets when I walked in, but here's a clip of what the lamination process looks like. Once it's laminated, we move over to the laser machine to develop the image on top of the board.
This is the board already with the film. You can see there is no pattern right now. Yeah. Okay, the pattern. There's a pattern on the board right now.
And this pattern was, there's a laser in there that's marking this pattern onto the board.
Yes,
okay.
Correct. This part still keeps the dry film. So this part need to remove the dry film to show the original color of this board.
And so for the lasering process, you need to protect it, but not anymore after that.
Yeah.
You can remove this.
Yeah,
is that what he's peeling off now?
This is a protective film.
So we have two films.
Yeah.
She goes on to explain that the clear film that's being peeled off is just a protective layer for handling. And underneath, there's a dry film that was just developed with the laser. But there's still some undeveloped film on the board, and that gets washed off in this next step. So when you get done washing off the undeveloped film, you end up with a negative, if you will, of the places where you want the electroplating to occur. It looks something like this.
Upstairs is the pattern image. Once that's finished, then it will go to the planting. The planting is to add more copper. Planting line finish, and it will go to downline etching.
So it goes here first.
Yeah, goes here first,
okay.
And then downline.
And then over here to the etching.
Yeah. Okay. Wash. Actually, each section is a different chemical solution. This is tap water, and this is a tap water with some chemical to remove the oil.
After we finish this series of degreasing, cleaning, electroplating, cleaning again, they also add a layer of tin on top to keep the copper from oxidizing and to protect it during the next step where they start to remove the hardened film. Earlier I told you we baked an image onto the board. So the board is covered everywhere that we don't want copper to deposit. When we dip it into these various solutions, we're now electroplating the copper onto the board everywhere that we want the traces to be in the final design. The timing of each step is really important to build up exactly the right amount of copper as specified by the design.
This step, we need to remove the blue one.
So the white part is the part that remains.
Yeah.
Okay, and the blue is what gets removed.
Yes, correct.
Okay.
This is the blue. The blue came out of the board.
Oh, okay,
Yeah.
Yeah.
Jeremy, you can see the board. 可以拿一个下来给他看一下吗？
可以。
Oh, okay. Jeremy, you see, all these are supposed to be blue, right? And right now the blue will go.
Yeah.
And this是镂铜的，对吧？
对对对。
Okay, yeah, this is the copper. You know, this area, the copper was removed.
Okay.
This is the color of the substrate. This green area is the color of the substrate, and all the white part is the tin.
Okay.
The tin is to protect the circuit.
Okay.
Yeah. So the final step is to remove the tin.
Now, the first time I heard her say this, I didn't understand what she meant. She said we were going to remove the copper, but obviously we want to keep the copper, right? So we've already removed the blue, which is this layer, but the copper she's talking about removing is this copper down here. We want to remove these two layers, except in the area where we want to preserve the traces. So once we remove the additional copper, it looks something like this. The copper here was protected by this layer of tin, which is what she was describing a minute ago. And now the final step is to remove this tin, and we will have the final design. All of this area being non-conductive and only having the copper traces exactly where we want it.
You see, this area over supposed to be the white. Right now the tin is moved. It's moved. So this is the copper. 这是铜的，对吧？对的。So this is the copper. And this is the green, or the yellow part is the substrate color. Once etching finished, it goes to AOI.
AOI stands for Automatic Optical Inspection. Basically, these machines will scan the whole board and compare that to the original files. If there's anything out of place, any copper that has joined in a place that it shouldn't join, they have little razor blades where they can scratch off those tiny little imperfections. There are actually several quality control steps like this because it allows you to repair the board when the repair is very easy instead of scrapping a lot of boards. If they need a major repair, they can send it to another department. And even if it can't be repaired, they've already prepared for this by fabricating a few extras when they were assembling this from the beginning. That way they take advantage of the economies of scale and they can still meet the customer's even if they have to scrap some.
So in this section, it is for multi-layer.
So far, we've only looked at single-sided or double-sided PCBs, but if you have a multi-layer PCB, you need to make all of the inner layers first. Manufacturing of the inner layers is very similar to the outer layers, so I wanted to show you that first. There are some differences in the way they image the board. For example, they cover the copper that they want to keep, then etch away the unwanted copper. Also, some of the layers are solid copper serving as a ground layer or a power layer, and when you drill the holes through, that gives you access to the power plane or the ground plane. This part is really interesting to me because it's a very clever way to reduce interference. See, if you have all the power lines going across the top of the board, every time you send power, there's a magnetic field produced around the copper trace, and that interferes with the other copper traces. But cleverly, if you send the signal straight down, not only can you make the board smaller and more compact, the interference is gone. Now, just like everything in engineering, there are pros and cons here. The complexity is definitely going up, which is increasing the cost. And there's some other clever benefits that we haven't talked about yet, but this is getting way outside of the scope of this video, so let's move on. Here we can see him assembling one of the inner layers. Basically, there's a PCB, which has a yellow material coated on top. That's an adhesive layer. And then they're gonna put this copper foil on the top and on the bottom. All of this gets sandwiched between two metal sheets, and that'll go into the next room, wherein this entire assembly will be put into a pressurized heated chamber. The heat and pressure is important because that makes sure you get good adhesion, that there are no voids in between the layers, and then all of this is squished in an enormous press to seal it all up nice and tight. And you end up with this copper foil looking plate with a PCB inside. Because it just looks like a big copper sheet, we need to properly locate all the holes so that each layer can be lined up with the one that goes on top of it. And that's what this machine does. It's an X-ray machine that allows you to look through the copper foil, find those alignment holes, and then they can use that to stack all of these PCBs together and then do one final seal to combine all of the PCB layers. Once all the layers have been combined, it jumps back in the process where all the other PCBs are because they do the outer layer last.
You know, the appearance of the PCB, you know, you need to color the board. So that's what we're gonna do check.
Oh, okay.
Okay.
I can smell the inks.
Yeah. This is our solder mask line. You know,
Solder
you can,
mask. Solder mask,
a solder mask line. So like the clothes of the PCBs.
Oh,
The clothes of the
clothing on the
PCBs.
PCB.
Yes.
I like it, yeah. The solder mask is this green layer you see on top of the board, which she just described as the clothing for the PCB. The solder mask not only keeps the copper from oxidizing, but it also protects the board so that when you solder on the components, the solder only sticks exactly where you want it to stick.
So this line is, you know, manually. Like we usually use it for like prototype orders, like 5 pieces, 10 pieces. We will use Yes,
Okay.
if it's for bulk orders, large orders, then it will come to these machines, and these machines will process the solder mask part. Like this worker, and he's doing the board, you know, with green colors.
Okay.
Yeah.
So I can see, okay, and then you have the wipers there rubbing
Right. They are scraping.
solder mask on.
Scraping the green oil, green solder mask onto the board.
Okay.
Yeah, so you can see this is before solder mask, and this is after.
this one is after.
Yeah. And after all the, you know, this is finished, it will send to the oven to dry the board because this is wet.
How long does it need to dry?
Wait a sec, I need to check with Manager.
Okay.
他说这个放的那个烤箱里面烤干要多久啊？
我们这个是烤的18分钟左右。
Okay, about 18 minutes. Yeah, you got it.
Yeah.
18 minutes. This is the ovens to dry the boards with solder mask.
After they've baked on the solder mask, they go to another screen printing room that will put all the writing on the PCB. So they have several machines that can do this. Some of them are like laser printers, and some of them use the same screen printing process we just watched with the green solder mask. The most impressive thing might be how many steps there are. I had no idea a PCB went through so many processes before it was ready.
This e-testing line, high flying needle test line. Yeah, it's e-testing.
It's checking for open and closed circuits?
Yeah, right. Short or open. And all the connections are intact or not.
This was definitely the most interesting quality control step. These little needles fly all over the board, probing every pin on the board to confirm that all the circuits work as they should. And this is designed specifically for prototype boards where they haven't made very many. If they want to test thousands and thousands of boards, this process is actually kind of slow. So they have a different quality control test that they call bed of needles. The bed of needles is kind of like a fixture in CNC machines where it's pre-designed specifically for that board. So there's a needle for every pin on the board, and you put the entire board on top of the bed. Every pin is tested pretty much instantly, and you can take it off. And this allows them to test thousands and thousands of boards much more rapidly. But of course, to make that bed of needles is kind of expensive, so it only makes sense to do this when you're testing a lot of boards. Economies of scale. After this final quality control check, the boards are ready to be separated from each other. So we go to the milling department, cut out the individual PCBs, and then finally we're ready to package these boards for the customer. I've been designing and building with electronics for quite a long time, and many of my projects, including my robot, are quite complex. They certainly would have benefited from me designing my own PCB, but I've never actually considered doing it. I would just buy something close enough and plug and play, if you will. But seeing the engineering that goes into making a PCB and also the reality of how accessible this is, I think I'm going to give it a try. Maybe you'll see some PCBs in my future projects. We'll see. Well, thank you so much for joining me on this tour. I have a couple of more factory tours that I did while I was in China, you know, efficiency and all that. So like, subscribe, all that good stuff if you want to see more videos. It really helps the channel out, and it is the only way for you to know when I've released a new video. Thank you so much, patrons and YouTube members. You guys are a big part of helping me keep this kind of thing going, and I'll see you in the next video. Thanks for watching.